Okay, well, I thought I would make a solution to number 11. But it is nearly the same as number 10. And it is also done in the Friday Zoom session. A couple of you have asked, and I've been sending that link to it. But I finally just decided, well, maybe instead of, excuse me, maybe instead of just keep sending that link, I'll just make a solution. I just did number 10, so I might as well do number 11 here. And there's a nice little picture. Let's see if I can semi-repeat it. It shows a bottom half of a hemisphere with a small charge sitting a very small distance. They call it delta. Then they say take delta as it goes to 0. I guess the hemisphere also has the symbol R here for the radius. But this charge here is Q. And so the particle of charge Q is located immediately above. So it's just microscopically above, really, really close in the limit. So kind of a calculus thinking here. Above the flat hemisphere. And the first part of it says, what is the electric flux? And then A through the curved part, and then B through the flat part. And so, as I was saying, this is a lot like number 10, because if I were just to draw Q over to here, and maybe draw the electric field, and instead of putting a hemisphere around it, I put a whole sphere around it. Then you could see that all of the flux coming from that charge would go through the whole sphere. And again, going back to number 10, we learned this, that if you ever take a closed surface, and so this over here is a closed surface, and you add up all the flux, that is, you add up all the electric field going through that, you will get the charge inside over epsilon naught. So instead of actually doing any integral here, I'll just say, look, in this red Gaussian surface, this sphere, I would get Q, because that's the charge enclosed over the permittivity of free space. So that's the total flux coming from here. Now, the key to the problem then is to come back to the real picture and realize, okay, so this flux is going up and down, and the stuff that's going up is half of it, and the stuff that's going down is the other half. And so looking at, say, and I'll do B first, because B says, what is the flux through the flat face? I would say then that, again, if we're microscopically close, anything that has a slight downward angle to it will go through this flat circle of the, what I'll call the top part of the hemisphere. So that would be half of it. So I would just write 1/2 Q over epsilon naught. They don't give me a number for Q, so I'll just leave it there. And, of course, then A, again, a visual effect is that, okay, now look, A is just saying this, that the whatever goes in here comes out there. Oh, by the way, let me go back to B. I apologize. Stuff going in is negative. Stuff coming out is positive. That's what we see from this dot product. Okay, so I should have put a negative there. But then to answer A, I would say it's coming out, so it's positive, but it's the same number. What goes in must come out. I suppose another way of saying that same thing is back here in this equation, Gauss's law, because if you if your surface that you're doing your integral on is the hemisphere, not the sphere. Now, when I did the sphere, there was a charge enclosed. But if I would take the same logic to this hemisphere, this charge is not actually enclosed. So an integral of E dot dA would be 0 for this hemisphere. And of course, again, maybe visually and hopefully visually you can see that, because what goes into this top flat part comes out the rounded part. So, yeah, it does equal 0. And of course, that's what you would get if you added up these two flux. This is the negative, this is the positive. You add those together, you get 0. And so that was kind of the thinking, and trying to give you some visual understanding of flux so you can eventually use it to do some harder problems to get the electric field. But you got to kind of understand flux first.